The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So let's start right away with stuff that we will need to see before we can go on to more advanced things. So hopefully yesterday in recitation you heard a bit about vectors. How many of you actually knew about vectors before that? Okay, that's the vast majority. If you're not one of those people, well, hopefully you will learn about vectors right now. I'm sorry that the learning curve will be a bit steeper for the first week, but hopefully you will adjust fine. If you have, trouble with vectors, do go to your instructors, recitation instructors' office hours for, extra practice if you feel the need to. You'll see it's pretty easy. So, just to remind you, a vector is a quantity that has both a direction and a magnitude or length. So, concretely, the way you draw a vector is by some arrow like that, okay? And so it has a length, and it's pointing in some direction. And so now the way that we compute things with vectors typically is we introduce a coordinate system. So if we're in the plane x, y axis, if we're in space x, y, z axis, so usually I will try to draw my x, y, z axis consistently to look like this. And then I can represent my vector in terms of its components along the coordinate axis. So that means when I have this arrow, I can ask how much does it go in the x direction, how much does it go in the y direction, how much does it go in the z direction. And so, for example, let's call this vector A. So a small convention, when we have a vector quantity, we put an arrow on top to remind us that it's a vector. If it's in a textbook, then sometimes it's in bold because it's easier to typeset. If you've tried, in your favorite word processor, there's bold is easy and vectors are not easy. So the vector, you can try to decompose in terms of unit vectors directed along the coordinate axis. So the convention is there's a vector that we call I hat that points along the x-axis and has length 1. There's a vector called j hat that does the same along the y-axis, and a k hat that does the same along the z-axis. And so we can express any vector in terms of its components. So the other notation is a1, a2, a3 between these square brackets. Well, maybe I should say angular brackets. So the length of a vector we denote by, if you want, it's the same notation as the absolute value. So that's going to be a number, or as we say now, a scalar quantity. Okay, so a scalar quantity is a usual numerical quantity as opposed to a vector quantity. And its direction is sometimes called dir of A, and that can be obtained just by scaling the vector down to unit length. For example, by dividing it by its length. Okay. So well, there's a lot of notation to be learned. So for example, if I have 2 points, P and Q, then I can draw a vector from P to Q, and that vector is called vector PQ. Okay? So maybe we'll call it A. But a vector doesn't really have necessarily a starting point and an ending point. Okay? So if I decide to start here, and I go by the same distance in the same direction, this is also the vector A. It's the same vector. So a lot of vectors will draw starting at the origin, but we don't have to. Okay? So let's just check and see how things went in recitation. Where did I put it? So let's say that I give you the vector 3, 2, 1. And so what do you think about the length of this vector? Okay, I see an answer forming. So a lot of you are answering the same thing. Maybe I shouldn't spoil it for those who haven't done it yet. Okay, I think the overwhelming vote is in favor of answer number 2. I see some 6s. I don't know. That's a perfectly good answer too. But hopefully, in a few minutes, it won't be I don't know anymore. So let's see. How do we find the length of a vector 3, 2, 1? Well, so this vector A, it comes towards us along the x-axis by 3 units. It goes to the right along the y-axis by 2 units. And then it goes up by 1 unit along the z-axis. Okay, so it's pointing towards here. That's pretty hard to draw. So how do we get its length? Well, maybe we can start with something easier, the length of a vector in the plane. So observe that A is obtained from a vector B in the plane. Let's say B equals 3i hat plus 2j hat. And then we just have to still go up by 1 unit. Okay? So let me try to draw a picture in this vertical plane that contains A and B. If I draw it in the vertical plane, so that's the z-axis, that's not any particular axis, then my vector B will go here, and my vector A will go above it, and here that's 1 unit, and here I have a right angle. So I can use the Pythagorean theorem to find that length A squared equals length B squared plus 1. Now, we are reduced to finding the length of B. But the length of B we can again find using the Pythagorean theorem in the xy plane, because here we have a right angle, here we have 3 units, and here we have 2 units. Okay, so if you do the calculations, you will see that, well, length of B is square root of 3 squared plus 2 squared, that's 13, so square root of 13. And length of A is square root of length B squared plus 1 squared, if you want, which is going to be square root of 13 plus 1 is square root of 14. Hence, answer number 2, which almost all of you gave. Okay, so the general formula, if you follow what we did, in general, if we have a vector with components A1, A2, A3, then the length of A is the square root of A1 squared plus A2 squared plus A3 squared. Okay, any questions about that? Yes?
Does this pattern continue for values above A3?
Yes, so in general, we indeed can consider vectors in abstract spaces that have any number of coordinates, and then you have more components. In this class, we'll mostly see vectors with 2 or 3 components only, because they are easier to draw, and because a lot of the math that we'll see works exactly the same way, whether you have 3 variables or a million variables. If we had a vector with more components, then we would have a lot of trouble drawing it, but we could still define its length in the same way by summing the squares of the components. So I'm sorry to say that here, multivariable, multi will mean mostly 2 or 3. But be assured that it works just the same way if you have 10,000 variables. Just calculations are longer. Okay. More questions? No? Okay. So what else can we do with vectors? Well, another thing that I'm sure you know how to do with vectors is to add them or to scale them. So vector addition. So if you have 2 vectors, A and B, then you can form their sum A plus B. How do we do that? Well, first, I should tell you, vectors, they have this double life. They're at the same time geometric objects that we can draw like this on pictures, and they're also computational objects that we can represent by numbers. So every question about vectors will have 2 answers, one geometric and one numerical. Okay, so let's start with the geometry. So let's say that I have 2 vectors, A and B, given to me. And let's say that I thought of drawing them at the same place to start with. Well, to take their sum, what I should do is actually move B so that it starts at the end of A, at the head of A. Okay, so this is again vector B. So observe, this actually forms now a parallelogram, right? So this side is again vector A. And now, if we take the diagonal of that parallelogram, this is what we call A plus B. Okay, so the idea being that to move along A plus B, it's the same as to move first along A and then along B. Or along B, then along A. A plus B equals B plus A. Okay, now if we do it numerically, then all you do is you just add the first component of A with the first component of B, the second with the second, and the third with the third. Okay, say that A was A1, A2, A3, B was B1, B2, B3, then you just add this way. Okay, so it's pretty straightforward. So, for example, I said that my vector over there, its components are 3, 2, 1, but I also wrote it as 3 times I plus 2 times j plus k. What does that mean? Oh, so I need to tell you first about multiplying by a scalar. So maybe I should say this is about addition. So multiplication by a scalar, it's very easy. If you have a vector A, then you can form a vector 2A just by making it go twice as far in the same direction. Okay? Or we can make half A more modestly. Or we can even make minus A, and so on. Okay? So now you see if I do the calculation 3 times I plus 2 times j plus k, well, what does it mean? 3 times I is just going to go along the x-axis, but by distance of 3 instead of 1. And then 2 times j goes 2 units along the y-axis, and k goes up by 1 unit. Well, if you add these together, you will go from the origin, then along the x-axis, then parallel to the y-axis, and then up. And you will end up, indeed, at the end point of the vector A. Okay. Any questions at this point? Yes?
So for the geometric vector addition, basically just using the tip to tail addition?
Exactly. To add vectors geometrically, you just put the head of the first vector and the tail of the second vector in the same place, and then it's head to tail addition. Any other questions? Yes?
So when you're subtracting, you just put one in another direction?
That's correct. If you subtract 2 vectors, that just means you add the opposite of a vector. So for example, if I wanted to do A minus B, I would first go along A and then along minus B, which would take me somewhere over there. Okay? So A minus B, if you want, would go from here to here. Okay. So, well, hopefully you've kind of seen that stuff either before in your lives or at least yesterday. So I'm going to use that as an excuse to move quickly forward. But